Have you ever looked at the universe and wondered, what are the rules? Is there a master blueprint that dictates how everything works, from the tiniest particles to the largest galaxies? Well, physicists have been on this quest for centuries, and they've uncovered some truly fundamental constants of nature. But one number stands out as particularly mysterious and profound. It's called the fine structure constant, and it's arguably the most important number in all of physics. So, what is this number? The fine structure constant, often represented by the Greek letter alpha, is approximately 1 over 137. That's it. Just a simple dimensionless number. But don't let its simplicity fool you. This number governs the strength of one of the 4 fundamental forces of nature, the electromagnetic force. Think about it. Electromagnetism is everywhere. It's the force that holds atoms together, creating molecules, which in turn form everything you see around you. The chair you're sitting on, the screen you're watching, and even your own body. It's responsible for light, electricity, magnetism, and most of chemistry. And the strength of all these interactions is determined by this one single number, alpha. If alpha were just a little bit different, the universe would be unrecognizable. If it were smaller, the electromagnetic force would be weaker. The nuclei of atoms wouldn't be able to hold on to their electrons as tightly. This would make stable atoms much larger and the bonds between them much weaker. Complex molecules, like the DNA that carries our genetic code, simply couldn't form. Life as we know it would be impossible. On the other hand, if alpha were larger, the electromagnetic force would be stronger. Electrons would be pulled much closer to the nucleus. This sounds like it might make things more stable, but it actually creates a bigger problem. The repulsion between the positively charged protons in the nucleus would become so intense that it would overcome the strong nuclear force that holds them together. Any atom with more than a handful of protons would immediately fly apart. The periodic table would be drastically shorter. Stars wouldn't be able to forge heavy elements through nuclear fusion. No carbon, no oxygen, no iron. The universe would be a boring place, made almost entirely of hydrogen. So, this value of roughly 1 over 137 seems to be perfectly tuned for a universe that can support complexity, structure, and life. This has led many physicists and philosophers to wonder why this specific number. Is it a complete accident, a random roll of the cosmic dice? Or is there some deeper reason why it has to be this value? This is one of the biggest unsolved mysteries in physics. The story of the fine structure constant begins in the early 20th century with a physicist named Arnold Sommerfeld. At the time, Niels Bohr's model of the atom was the latest and greatest thing. It pictured electrons orbiting the nucleus in neat circular paths, like planets around the sun. But this model had its limits. When scientists looked very closely at the light emitted by atoms, they saw that the spectral lines, which were supposed to be single, sharp lines, were actually split into several finer lines. This was called the fine structure. Sommerfeld realized that to explain this, he needed to refine Bohr's model. He incorporated Einstein's theory of special relativity, suggesting that electrons weren't just in simple circular orbits, but could be in elliptical orbits as well. And because the electrons were moving at incredible speeds, their mass would actually change depending on where they were in their orbit, just as relativity predicts. When Sommerfeld did the math, a new number popped out of his equations. This number determined the size of the splitting in the spectral lines. He called it the fine structure constant. What made it so remarkable was that it was a pure dimensionless number. It didn't have units like meters or seconds. It was formed by combining 3 other fundamental constants: the charge of an electron, the speed of light, and Planck's constant. It was a beautiful combination of electromagnetism, relativity, and quantum mechanics, the 3 great pillars of modern physics at the time. The legendary physicist Richard Feynman was famously obsessed with this number. He called it one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. He even had the number 1 over 137 on his license plate. Feynman believed that if we could truly understand where this number comes from, it would unlock a much deeper understanding of the universe. So, what are the modern theories? Where could this magic number come from? One of the most ambitious goals in theoretical physics is to create a theory of everything. This would be a single unified framework that describes all four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces, as different aspects of one single underlying force. Many physicists working on things like string theory or loop quantum gravity hope that their theories will one day be able to calculate the value of alpha from first principles. In these theories, the constants of nature aren't arbitrary. Instead, they are determined by the very geometry of spacetime itself, perhaps by the way extra hidden dimensions are curled up. If we could figure out that geometry, we might be able to derive alpha and all the other constants directly. That would be an incredible breakthrough, telling us that the universe isn't random, but has a deep underlying mathematical logic. But there's another, more mind-bending possibility: the multiverse. The idea here is that our universe is just one of countless universes, each with its own set of physical laws and constants. In this scenario, there's no deep reason why alpha is 1 over 137 in our universe. It's just a lucky accident. We just happen to live in one of the rare universes where the constants are just right for life to evolve. In all the other universes with different values for alpha, no one is around to observe them. This is known as the anthropic principle. It's a controversial idea because it's very difficult to test, but it's a fascinating solution to the fine-tuning problem. So, we're left with this profound mystery. Is the fine structure constant a clue pointing towards a deeper, unified theory of physics? Or is it evidence that we live in a vast multiverse and we just got lucky? We don't know the answer yet. But the story doesn't end there. Another fascinating question is, has alpha always been the same? For most of the history of physics, the fundamental constants were assumed to be, well, constant, unchanging throughout all of space and time. But what if they're not? What if the laws of physics themselves can evolve? In the late 1990s, a team of astronomers made a startling claim. By analyzing the light from distant quasars, extremely bright galactic cores billions of light years away, they found evidence that the fine structure constant might have been slightly different in the distant past. Since the light from these quasars has taken billions of years to reach us, we're essentially looking back in time. Their measurements suggested that about 10 billion years ago, alpha was a tiny bit smaller than it is today. This was a revolutionary idea. If true, it would completely change our understanding of cosmology and fundamental physics. It would mean our current theories, like the standard model of particle physics, are incomplete. However, science is a rigorous process. These results were incredibly difficult to obtain, and other teams of scientists, using different telescopes and methods, have tried to replicate them. Some studies have found similar results, while others have found no change at all. The jury is still out. The measurements are at the very edge of our technological capabilities, and there are many potential sources of error. But the quest continues. Scientists are building even more precise instruments, like atomic clocks, to measure the value of alpha here on Earth with unprecedented accuracy. If they can detect even the slightest change over a few years, it would confirm that the constants are not truly constant. This search for a varying alpha is one of the most exciting frontiers in modern physics. The fine structure constant, alpha, is more than just a number. It's a symbol of both what we know and what we don't know about the universe. It connects quantum mechanics, relativity, and electromagnetism in a single, elegant expression. Its value appears to be exquisitely fine-tuned to allow for the existence of stars, planets, and life. And it might not even be constant, potentially changing over the vast expanse of cosmic time. The mystery of 1 over 137 continues to inspire and challenge physicists around the world. As Richard Feynman said, it is a number that all good theoretical physicists should have, stuck on their wall and worry about. And as we continue to probe the universe with more powerful tools and more brilliant ideas, we get closer to understanding this magic number, and in doing so, understanding the very fabric of reality itself. Thanks so much for watching. If you enjoyed this journey into the mysteries of physics, be sure to hit that like button and subscribe for more deep dives into science. Let me know in the comments what you think. Is alpha a clue to a theory of everything, or just a lucky number from the multiverse? I'd love to hear your thoughts. See you in the next one. If alpha does vary, the implications are staggering. It would mean the laws of physics are not fixed. The fundamental constants we thought were eternal might be dynamical, influenced by fields or conditions we do not yet understand. It would open the door to new physics, perhaps a deeper theory that explains not just the value of alpha but its evolution. On the other hand, if alpha is truly constant across all time and space, that is equally mysterious. Why should this particular number be frozen into the structure of the universe? What enforces its constancy? Either answer leads to profound questions. Let's consider what it would take to explain alpha. In an ideal world, a complete theory of physics would have no free parameters. Every number would be calculable from the theory itself. The masses of particles, the strengths of forces, the speed of light, all would emerge from the mathematics as inevitably as pi emerges from the geometry of a circle. But our current best theories are nowhere near this ideal. The standard model of particle physics, which describes all known particles and 3 of the 4 fundamental forces, contains about 20 free parameters. These include the masses of the quarks and leptons, the strengths of the forces, and mixing angles that govern how particles transform into one another. The fine structure constant is one of these parameters. To calculate it from first principles, you would need a deeper theory, something beyond the standard model that derives the standard model's parameters as consequences of a more fundamental structure. String theory is one candidate. In string theory, particles are not point-like objects, but tiny vibrating strings. The different vibrational modes correspond to different particles. The theory requires extra dimensions of space beyond the familiar 3. The precise way these extra dimensions are curled up, their geometry and topology, determines the values of the constants we observe in our 4-dimensional world. In principle, string theory could predict alpha. In practice, the number of possible ways to curl up the extra dimensions is vast, perhaps 10 to the 500 or more. This is the landscape problem. Each configuration gives a different set of constants, a different universe. Our universe, with its particular value of alpha, is just one point in this colossal landscape. Why we are here and not somewhere else is unknown. Some invoke the anthropic principle. Most configurations would not support complex chemistry or stable atoms, let alone observers. We find ourselves in a universe with this value of alpha because only such universes can produce beings capable of asking the question. This is philosophically unsatisfying to many. It feels like giving up on explanation and resorting to cosmic luck. But it might be the truth. Loop quantum gravity and other approaches to quantum gravity offer different perspectives, but none has yet delivered a prediction for alpha. The problem is hard. The fine structure constant sits at the intersection of quantum mechanics, electromagnetism, and relativity. To derive it, you would need a unified theory that seamlessly integrates all 3. We do not have that theory yet. And until we do, alpha remains an enigma, a number we can measure but not understand. Feynman also pointed out another troubling aspect. The value of alpha is suspiciously close to certain values that make the physics interesting. If it were much larger, quantum electrodynamics would break down. The perturbative methods we use to calculate interactions rely on alpha being small, much less than 1. At each order of approximation, you multiply by alpha, and because it is small, the higher order terms become negligible. This is why QED works so well. But if alpha were close to 1, perturbation theory would fail. The theory would become non-perturbative, much harder to solve. Interestingly, the strong nuclear force, which binds quarks into protons and neutrons, has a coupling constant that is close to 1. That is why quantum chromodynamics, the theory of the strong force, is fiendishly difficult. Alpha's smallness makes electromagnetism calculable. Is that an accident? Or is there a reason the universe is set up this way? We do not know. There is also the question of the electron's charge. Alpha is built from the charge of the electron, the speed of light, and Planck's constant. Why does the electron have the charge it does? In quantum field theory, charge is a fundamental property, but its value is not derived. You put it in by hand. Some grand unified theories attempt to relate the charges of different particles and the strengths of different forces. In these theories, at very high energies, the electromagnetic, weak, and strong forces merge into a single unified force. The running of the coupling constants, the way their effective strengths change with energy, hints at this unification. If you extrapolate, the 3 forces seem to converge at an energy scale around 10 to the 16 GeV, far beyond what any collider can reach. At that scale, alpha and the other constants might be determined by a single underlying parameter. But this is speculative. The extrapolation depends on assumptions about particles and interactions we have not discovered. And even if grand unification is correct, it would explain alpha in terms of another parameter, pushing the mystery back but not eliminating it. Feynman suggested that perhaps the right question is not why alpha has this value, but whether there is a principle that selects it. Is there a consistency condition, a requirement that the universe must satisfy, that forces alpha to be what it is? Some have explored the idea that the constants are constrained by the requirement that the universe be capable of self-observation, a kind of cosmic self-consistency. Others have looked at whether mathematical beauty or simplicity might select certain values. None of these approaches has yielded a definitive answer. The fine structure constant remains stubbornly mysterious. Interestingly, alpha appears not just in atomic physics but in unexpected places. It shows up in the quantum Hall effect, a phenomenon in condensed matter physics where the Hall conductance of a two-dimensional electron gas is quantized in units involving alpha. It appears in the Josephson effect in superconductors. It governs the rate of spontaneous emission of photons from atoms. It is ubiquitous, a thread running through the entire tapestry of physics. This ubiquity suggests it is fundamental, not a quirk of one theory, but a deep feature of how the universe is built. One of the most striking things about alpha is its dimensionlessness. It has no units. It is a pure number. Most constants in physics have units. The speed of light is meters per second. Planck's constant has units of action. But alpha is just a number, the same in any system of units. This makes it special. Dimensionless constants are the ones that truly characterize a universe. You can imagine aliens on the other side of the galaxy. They might use different units for length and time, but if they measure the fine structure constant, they will get the same number we do. It is a universal fingerprint, a signature of our cosmos that any intelligent observer would recognize. Feynman once mused about what he would ask if he could pose one question to an all-knowing oracle. He said he might ask for the value of alpha, or rather, the reason for its value. Of all the mysteries, this one seemed to encapsulate the frustration and wonder of physics. We have deciphered so much. We can predict the outcome of particle collisions, the spectra of stars, the quantum behavior of matter. But this one number, this simple ratio, eludes us. It is a reminder that for all our progress, we are still missing something fundamental. There is a layer of reality we have not yet touched. Some physicists hold out hope that a theory of everything, a final unified framework, will explain alpha and all the other constants. Perhaps in that theory, there will be no free parameters at all. Everything will be determined by pure mathematics, and the constants will emerge as inevitably as the digits of pi. Others are more skeptical. Perhaps the constants are environmental, set by the particular way our universe crystallized out of the quantum foam, and other universes in a multiverse have different values. In that case, we will never derive alpha. We can only measure it and acknowledge that we live in a universe where it happens to be 1/137. Richard Feynman did not live to see a resolution. He died in 1988, still puzzled by alpha. In the decades since, we have measured it more precisely, tested it more thoroughly, but the mystery has not lifted. If anything, it has deepened. The fine structure constant stands as a monument to the limits of our understanding, a simple number that encodes the strength of all electromagnetic interactions, the foundation of chemistry, the essence of light, and the boundary between what we know and what we do not. It is a challenge, a provocation, and a promise. Somewhere in that number is a secret, a clue to the deeper workings of reality. And until we unlock it, the fine structure constant will remain what Feynman called it, a magic number, with no understanding by man, waiting for the insight that will finally reveal why the universe chose 1/137.